Okay. All right, I think I'm back on the stream. Yep, I'm back on the stream. So for those who don't know, yeah, let's start then. Okay, so the first problem you have here was here we go. Let's move on to this. Okay, the first problem you have is a refraction problem. Okay, I think we've seen this on stream before, but of course we'll just go through the problem one by one here. Okay, so the first problem is about the refractive index of light. From x to y is 4/3, and then from y to z is 3/5. Okay, what's a refractive index for light traveling from x to z? Okay, now there is the proper way to do this is to go back to the definition of the refractive index. This would be n, and we know that n would be equal to why is it not writing? Okay, there we go. Fixed. Okay. Okay. So we know by definition that this refractive index n, this is going to be c over v, right? Okay. Now, because it's c over v, then that means okay, let's write that again, c over v. So what we're going to do now is we're basically just going to do nx would be equal to c over vx, let's just label it like this, and y is equal to c over vy, and then nz will be equal to c over vz, right? So you can already see that because they all have this common term c, they can kind of cancel out. So from x to y, we're going to do nx over ny, right? And that's going to be equal to 4/3. And that's also going to be equal to c over vx over c over vy. And that's going to simplify, the c's cancel out, and that's going to simplify into vy over vx. So we don't have to actually solve for everything anymore. We kind of see a pattern, right? So 4/3 will be equal to vy over vx already, right? Okay. So now what's gonna happen? So what's gonna be v, so let's do it the other way around. What is gonna be let's put nx over ny here, right? So what's gonna be y over nz? So if we just put if we just extend that idea, ny over nz, it's gonna be the same idea. That's gonna be 3/5, and that's gonna be vz over vy, right? Okay. Now finally we're looking now for x to z, right? So nx over nz, we're gonna look for that. So basically what we'll do here is we're gonna do nx over ny here, then ny over nz rather, right? Okay, this ny cancels out, but we know that actually we don't have to do that because we know that nx over ny, we know that to be 4/3 here, and we know that ny over nz is 3/5. So that's gonna give us 4/5, right? That's all we need to know now. Done. So our final answer, A. Okay. All right. We actually didn't even need to know the vy over vx and vz over vy, but just in case we needed it, it's ready. So we just do it either way. Okay.
Yeah.
All right. Any questions for this problem?
No, not for now.
Okay. So this one's pretty straightforward. Okay, let's go to the next one that you sent over. Let's do structure. Let's do all the multiple choice first. Okay, so the next problem here is you have a Doppler effect problem. So you have an observer moving at 20% of the speed of sound away from the source. And what is the correct expression of the perceived frequency? So here's the problem itself. Okay. Let's zoom in a bit so it's easier to read. Okay. If we go into the data booklet, I'm just gonna go into the relevant section of the data booklet now. Where is it? Doppler effect. Okay. There are two equations for the Doppler effect. The good thing for you now in the new syllabus is that it is indicated which formula is for the moving source and which formula is for the moving observer. Okay. I'm gonna put here an annotated version first. This is the formula. Just so we know, for the previous syllabus from 2016 to last year, there was no distinction between the moving source and the moving observer. They were just given the two equations, and then they had to figure out which one was which. Okay. Now, just so we're clear, again, this is gonna be f prime is the observed frequency. F here is the emitted frequency. Okay, or the initial frequency. U will be the U's will be the speeds of either the observer or the source. V would be the speed of the wave. Okay, so all we have to do is apply this and apply the necessary formula. Which one is moving here? The observer is moving, so we have to use this formula here. Okay, now our F is equal to F0. Okay, let's just do it like this now. So what does this mean? The observer is moving at 20% of the speed of sound. In other words, your UO is equal to 0.2 V. Okay. So now we can, and then V would be the sound, the speed of the sound. So sound source, speed V, right?
Yeah.
Okay. All we have to do now is plug in all of these into the formula. So F prime, or the observed frequency, will be equal to F0 times V plus or minus, okay, plus or minus 0.2 V all over V, and the V basically cancels out. So we're left with F prime is equal to F0 times 0.8, or F prime equals F0 times 1.2. Now, in fraction form, this will be, because we have fractions, right? So this is going to be 4/5, and then this is going to be 5/4. Right? We can already...
Wait, sorry.
Okay. Where'd you get lost?
How do we cancel both of the V's at the top?
Oh, okay. So, okay, let me just redo that then from that step, okay? All right. So mathematically, if you look at the numerator, the V is a common factor. So I'll just do it like that. F0, then V times 1 plus or minus 0.2 all over V, right?
Yeah.
So that cancels out. So we're left with F prime is equal to, again, 0.8 F0, or F prime equals 1.2 F0. Now, before we go back to the choices here, let's go back to one more key feature, away, right? Okay. Now, the easiest way to remember this, whether this, whatever the Doppler effect, whatever the motion is, okay, it's most easily remembered with personal experience. Now, when you see away, you always remember that when an ambulance or a car moves away from you, or think about it this way. I think it's easier to think about it this way. You have heard a really fast car drive past you. It's always high-pitched first and then low-pitched when it passes you, right? Basically, it goes meow like that, right? It's never the other way around. right? So when it's approaching you, it's always gonna be high pitched, and when it's going away, it's gonna be a low frequency. Okay, low F prime,
Mhm.
and then approach would be a high F prime. Okay. Now, having
Yeah.
said that, since it's now away, we want the lower F prime. So our answer is this. So which one is this in term relative to our choices? It's D. All right.
Okay.
Okay.
Yeah.
Again, the way I always remember which one is which, because you will always have two possible answers, is the car approaching and a very fast car passing you. Okay. All right.
Yeah.
All right. So this one's done. Let's take a look at another. That's circular motion, simple harmonic motion. Okay, energy. Okay, I'm looking for one more Doppler effect problem if there's one more. If not, let's move on to.
Oh, I think there's only one.
Okay, we only get those two, right? Okay, so let's move on to. Okay, let's start with this problem now. This one's a circular motion problem. This is the only circular motion problem we have here. So, okay. Right. Okay, here we go. So you have a car traveling clockwise around a circular track of radius r. So we're just looking for the magnitude of the displacement from x to y. Okay. Now, it may seem tricky, but it's actually easy to remember if you remember that displacement is always start to finish only, right? Displacement is point to point. Okay, point to point. So in other words, from x to y, this is our displacement right there. That's a displacement. Okay.
Right.
Okay, and you can calculate that displacement easily.
Oh. Yeah.
Yeah, so let's just do it for completeness. This is gonna be r. That's gonna be r. This is gonna be, let's say, d, right? And we know that d squared equals r squared plus r squared. Okay, Pythagorean theorem. And from here, d squared is equal to 2 r squared, and therefore d is equal to r square root 2. Hence, the answer is C.
Right.
Okay. All right. Okay. Anything you'd like to ask about that?
No, I calculated the circumference,
Oh,
and
okay.
that's why I got it wrong.
All right. Since you mentioned that this is gonna be properly the distance. Okay, traveled. Traveled. Okay. All right. Let's move on. Equipotential. Let's do the equipotential problems at the end. Okay, let's do the energy problems now for oscillations. Let's start with this first. Okay, let's start with a spring loaded with a mass M. Let's just put it here now. Okay, so we have the spring loaded with a mass M and it oscillates with simple harmonic motion. The amplitude is, at that time, the amplitude is A, the energy is E. So what's the total energy when the mass is increased to 3m and the amplitude is increased to 2a? What's the easiest way to do this? Okay. Okay. Um. Okay. Let me think about this for a while. Just give me a few seconds. All right. Amplitude.
Okay.
Okay. Let's also get the energy formula. Yep. Here we go. Okay. Okay. So let's copy a couple of formulas here from the booklet. This is gonna be useful for the upcoming problems as well. Okay, so whenever you see harmonic motion and energy, these are the two formulas you will look at. Okay, now okay, this is the total energy. Let's just label that again. This is total. This is just the potential energy. Okay, and then from here, the kinetic energy will be equal to. Let's use the convention here. The kinetic energy will be equal to ET minus EP. This is gonna be for assuming no loss of energy. No energy loss, okay? Energy loss. Okay, so in this case, this should be easy now, because all we have to do is, the mass. So let's just do it like this. E is equal to, um, okay, 1/2 m. By the way, I forgot this. X0, this is the same as amplitude. Okay.
Right.
All right. So in other words, since our amplitude here is A, all I'm going to do now is m omega squared A squared. Okay. That's the total energy for the initial state. Let's label that E. Then let's label the second energy. Let's label that E nu. Okay. That's going to be 1/2. 1/2. The mass is now 3m. Then omega, the frequency. Here's the thing. That's not gonna change. The frequency is not gonna change. Or is it? Hold on. Actually, it will. Or is it? Okay, let me double check that. But the amplitude, let's just put nu here so we don't get confused later. And then the amplitude is 3a at 2a, right? Okay.
Wait, sorry.
Go ahead.
Could you scroll down? Could you scroll down a little bit
Oh,
because I don't
sure.
see the latest.
All right. Okay, hold on. Let me scroll down. Okay, you can see it now, right? Now, here, this new angular frequency, here's the thing. If I'm not mistaken, okay, oh, okay. So, K is equal to M. Okay, so let me just double check something here. I'm not 100% sure on that. Simple spring constant. Okay. Period is... okay. Here we go. The next thing we need to now know is this omega. This is again the angular frequency, right?
Yeah.
Okay. Now, the problem with this particular question is we're not actually given angular frequencies, right? However, we can use that the angular frequency is 2 pi f, and also we're gonna use the fact that f is equal to 1 over the period. So this is the same as saying 1 over 2 pi over the period, right?
Yeah.
Okay, and here is where we can solve it properly. The period of a spring mass system is actually given as 2 pi times square root of L over G. Okay, now you can see here we don't need to solve for anything from here. All we can say here is it does not depend on the mass, right?
Yeah.
So if we move our way backwards, then that means omega also does not depend on, not dependent on mass, right? So in other words, our assumption earlier that we can just erase that label nu there and that our omega squares are equals, it's valid. Okay, then all we're gonna do now, all we're gonna do from here is take the ratio. Now when you take the ratio, what do we get? So what is E nu over E? That's going to be equal to, um, okay, let's just copy that again. 1/2 times 6m omega squared A. Okay, 1/2 times 6m omega squared A all over 1/2 times m omega squared A. Oops, hold on. I think I missed something. It should be A squared, right? So this should be squared here. So that's going to become 4. Okay. So I'll just write that as 1/2 times 3m omega squared times 4a squared. There we go. Okay, so so we are missing a 4. This should be, hold on, let's see this again. 3 times 4 should be 12. Okay, so this should not be 6. This should be 12. Then there's an a squared here. But you will see that basically everything else cancels out. The 1/2, the m, the omega squared, and the a. So from here, the new energy will be equal to 12 times the old energy. So going back to our choices, final answer is C. Okay, so that's the long way of doing it. I'll just discuss the short way really briefly here. Short way is, think about it this way. The energy is always, for a spring mass system, energy is proportional to the amplitude squared for spring mass system. Also, energy is proportional to m. Okay. So when you put those together, what happens? All I'm doing now is multiply 3 by 2 squared, or 3 times 4. That gives us 12. Okay, so that's a shortcut. The long way again is just using the formula booklet. Okay.
Okay.
All right. Any questions there?
Everything's clear.
All right, great. So let's move on. Next problem. This one's done. Energy. That's 2 questions together. Just together as well. Okay. Okay, let's do this one. Okay, here's the idea now. So the system, the first system is it's a single spring. The second system is parallel springs. Okay, same load is applied to both. What's the total elastic energy in the changed system? Okay, so let's label this real quickly. So again, this is gonna be the energy here is EP and the energy here is E. So what is E as a when compared to EP, right? Okay. Oops. Let's undo that. All right. So the way I think the easiest way to look at this here is, okay, this, let's say that this is the equilibrium position. Let's draw it like that, right? This is the equilibrium position x0. Okay. Actually, no. Let's just try equilibrium. Equilibrium. Okay. If that's the equilibrium position, and then this is the extension, x, right? We because of the fact that you have two springs in parallel, the force, the load is being distributed across the two springs. So each spring will have an extension of x over 2. Okay?
Right.
All right. Because of this, each spring, so let's put it here. Each spring in parallel, right? What's the word here? Carries. The word carry isn't correct. Okay. Um, is stretched. I'll just do it like this. Is stretched by x over 2. So reasoning, that means um each spring has energy equal to 1/4 EP, right? So that's each
Right.
spring, but there are two springs. So then from here, two springs, each at 1/4 EP, gives us B.
It's very simple, actually.
Yeah, it's pretty simple. Now, if you want to use the formula booklet on this, let me just check the formula again. You're still going to use the energy formula here, but okay. And then you're going to use the 1/2 m omega squared x squared formula. But the problem is you don't have an omega because it's not really oscillating. It's just stretched, right? So
Yeah.
this is a bit easier to think about it like this. Okay. This one's done. Any questions here?
No, it's very clear.
All right. Let's take a look at the last multiple choice problem here. Then we'll go through the next restructured problems afterwards. Okay, the last multiple choice problem is here. What's the phase difference between particles on a what's this, second harmonic standing wave? Okay. If we look at this carefully, if you really think about it, this really carefully, phase difference is just saying how much ahead one particle is compared to the other in terms of their oscillation. Okay.
Yeah.
Okay. But if you think about this, because this is a standing wave, when this goes down, this also goes down, right? And when this goes up, this also goes up, right? So in this case, x and y move perfectly in unison. Move in unison perfectly. And in the same direction. Always, right? Always in the same direction. So this key idea here means the phase difference is 0.
Oh.
So the answer
Okay.
is automatically 0. Okay. Now,
0.
Now if I added a point Z here and I added a point W here, so X and Y are, the phase difference is 0. W and Z, the phase difference is also 0. Okay. But if we compare X and Z, what do we get? That's 180-degree phase difference. Because they're never moving in the same direction. Okay? Okay, I'll just put it here. Never in the same direction.
And if y was a little bit off to like the left or right, they wouldn't be in the same phase difference. But how do we calculate it?
All right, here's the thing. In a standing wave, these are the only cases. We don't have any other phase differences. Okay. Now, if this were a regular traveling wave, then we would have a phase difference between x and y. So you have to look
Okay.
you have to look at whether they are traveling or standing. Now, to address that question, what if they were traveling waves instead of standing waves, right? So let's just do that real quick. This is x and y on a traveling wave, right? Okay, so that means after some time, the wave is gonna be a bit like this, right?
Yeah.
Okay, so where is x now? X is gonna be here. It moved, but here our y is still basically on the same spot. So that means so there is a span of time. Okay, span of time that x and y are moving together, and there's a span of time they're not. Okay, so let's just say that this span of time is t. Okay, t where x, y are moving together. I'll just write it like this, where x and y move together. Okay, and then the period is t. Period is big T, right? And let's just note it here that rest of time um not moving together, right?
Yeah.
Okay, I'm pretty sure this is not actually taught a lot. Okay, so just to give you an idea what phase difference, how we can calculate phase difference from here. The phase difference or can be thought of as being T over big T times 360 degrees. No, yeah, 360 degrees. Okay, you can think of it like this. In other words, if they're moving in perfect unison, that time they're moving together is also the period. So that's period over period times 360. That's a phase difference of 360, which is the same as saying phase difference of 0.
Huh.
Okay.
But even though they're moving in unison, they're still in different positions.
Yes.
So that's the same phase difference.
Yeah.
There's no phase.
There will not be a phase difference even if they were in different positions. An example of that would be let's draw that wave again, and I'm gonna draw like that. Okay, so this if that's my x and then this were my y, and that's the equilibrium position. These two are in different positions, right?
Yeah.
So basically, if I kind of do this now. Uh, okay, there. Something like this, yeah? So in this case, our x is now here. So it's going this way, and then our y is also now here. So because these two are still moving together, then their phase difference is, in this case, it's actually 360 degrees. But again, we can consider that to be 0 degrees, right?
Yeah.
Okay. However, if I'm going to pick a new point here, and I'm going to pick this as z, okay? So where does this go? It's now here. So now it actually went up, right?
Yeah.
Okay. Now, if you really look at these 2 points only, they will always be moving in opposite directions. So their phase difference is 180 degrees, which is evident from their locations on the waves. Sometimes it's obvious from the location of the waves, right? So like these. But what if it's not one of the more obvious ones? What if, for example, it's here? Let's say that's our point W. Then, in terms of the wave, all we have to look now is basically find this and find this whole wavelength and find this length, and we do the same thing. Okay, so what we can do here is the phase difference is equal to distance divided by wavelength times 360 degrees. Okay, if we look at it in this particular manner. Okay. All right. So I'll just label that the distance, I'll just label this as D, and I'll change that to D here. Okay. Now, whether it's about time or about, in terms of standing waves, let's just go back to standing waves. Standing waves, it's always going to either be 0 or 180 degrees. There are no other possible values. Okay. All right.
Okay.
All right. So this one's done. Anything else you'd like to ask?
For this one, that's it. I understood everything.
Okay. So let's go to equipotential. No, let's do that last. Okay. C and D. Okay, let's do this. Let's do this problem. This one is about a standing wave now. The one... Okay, let's just put it here. So the solid line represents a standing wave at time t, and the dotted line represents the same standing wave at some instant later. The dot is the equilibrium position of a particle in the pipe. Okay, so you have, in this case, this looks like a half open pipe, right? Indicates to the right and displacement to the left. Okay, so on the diagram, indicate a dot for... Okay, since P is equilibrium, this means that here, this went down, right? But remember, this indicates, let's just do it like this, left. And this up arrow indicates to the right. Okay, so let's note that there. So this means it's gonna be here. This is a good spot. Okay.
Wait, sorry.
Okay.
Maybe it's a stupid question, but I don't understand how P and the wave are connected and why P would
actually, I was just so you know, that's not a stupid question. For one reason, this is the most difficult to visualize without... Okay, so all right, let me show you what's happening here. Okay, before we go anywhere else, remember that this particular particle here, let's just mark a few points first before we do anything. Remember that this is a node, right? And therefore this should be your antinode here.
Yeah.
Okay, so what do we know here? P is between the node and the antinode, so we know that P will oscillate. So whatever particle here, this will oscillate. Okay, but it won't oscillate as much as the particle near the antinode. Not as much as antinode. Okay, so in other words, this particle is going to oscillate, and I'm going to change it to blue. This particle is going to oscillate here like that. If this particle here at the antinode is going to oscillate like that. You get the idea?
Yeah.
So at the antinode, it oscillates more. At P, it oscillates, but not as much. Okay, so that's the first thing you can visualize from here. The second thing is that remember that actually no, there's something that I think there's a bit of missing info here. So anyway, part 1 can easily be answered because this this line represents position, right?
Yeah.
It simply means that here it goes that much, right? So this means this means goes to the left because of the way it's indicated in the text. So the proper position, and I'm gonna use which one? I'm gonna use green now for that. The proper position now for here, this is now where because it went to the left, that's where the position actually is. Okay. All right. Okay, the second part is a bit tricky. The velocity, right? Now remember that basically this is a graph, right? And that graph basically is you have a time and a displacement here, right? And what do we know if you have any kind of graph? How do we find the velocity? The velocity is equal to the tangent. Tangent equals velocity, right? Okay, so that's
Yeah.
the trick we're gonna do here. The trick now is that tangent is gonna be like so. We don't need to know its a value, but we need to know whether it's a positive or negative gradient or negative slope. We can see here that this is a negative slope, right? So meaning negative
Yeah.
velocity, negative v. So in other words, we can also say that v is going this way, to the left. Okay?
Okay.
All right. The second problem here, part D. Okay. So that's how you do the graph. Now let's kind of look at the problem itself, like solve some values, right? So the amplitude is given 4.2 millimeters, and the mass is 1.8 times 10 to the minus 6 kilograms. Yep. Okay. So in this case, we just use the formula booklet again. Okay, so once we put the formula booklet formulas in, we're looking for the energy. Again, I'll just copy this. Okay, just put the formula right here. Let's do that again. Okay, so which formula do we need here? We need only ET, right? Okay, so yep, all we have to do, plug this in. Change this to 4.2 times 10 to the minus 3 meters. And then what else do we need? The mass is already in kilograms. And then I think we can get omega is from the graph, right? From B. Do you have the graph for B there?
Wait, sorry, I'm not sure I understood.
Okay. Okay, hold on. Because here's the thing. The problem, we're given the mass already. This is checked, right? We're given the amplitude. Yeah. But we don't have the angular frequency. So we can't quite calculate what the total energy is. However, I'm going to guess that for the problem here, are you given a frequency somewhere or a period? If yes, then we can solve it.
Maybe it's possible because this was the second part of the question.
Yeah, I'm gonna assume it is. Now let's just see if there's anything else given. There's nothing else given in the stuff you gave me. So at this point, once you find, this is gonna be important. If you're given the frequency of the period, or the frequency or the period, then from here you can calculate omega, right? That's gonna be 2 pi f or 2 pi over t. And then this omega here is what you put into there.
Yeah, the frequency was 210 hertz.
Okay, there we go, 210 hertz. So let's do that here on the side, yeah? So if the frequency is 210 hertz, then omega will be equal to 2 pi times 210, right? Okay, yeah. And then finally we just find the energy. The energy will be equal to 1/2 Here, 1/2. The mass is, what's the mass again? Let's see. 1.6 times 10 to 1.8 times 10 to the
8
minus
times.
6.
Yeah.
10 to the minus 6 kilograms. Omega squared will be equal to 4 pi squared times 210 squared, right? And then a squared is 4.2 times 10 to the minus 3 squared. Okay. Right. In the interest of time, we're not gonna solve this, but you got the formulas now, right?
Yes.
Okay. The last problem here is displacement of P when the kinetic energy is equal to potential. So basically what you want to do here is all you have to do is that the kinetic energy is equal to 1/2 m omega squared x, and that's equal to 1/2 m v squared, right?
Yeah.
Actually, no, we don't need that bit. Okay. Also, we know x squared. Also, we know that this will be equal to what's the displacement we're looking for? That this is gonna be half of the total, so that's gonna be 1/4 et. Okay.
Yeah.
Sorry, not 1/4 et, 1/2 et. Okay, 1/2 et, because half of the energy will be in kinetic and half would be in potential. Okay. So if we do that, let's just finish the formula. Again, we're not going to solve for the interest of time. We're going to be left there with 1/4 times one, actually, no, let's just not do it like that. This is just going to be 1/2 times whatever this is. Okay.
Okay.
All right.
The energy.
Yeah. So that's the energy. Okay. We still have a couple of
Tasks.
tasks to do here, but I think we can do that tomorrow.
Yeah. No
All right.
problem.
Okay. Okay, I think, yeah, we'll just do that tomorrow. I'll in that case. So if you have anything else you'd like to ask, just add it for tomorrow. Okay.
Okay.
All right.
Thank you.
Thank you, and I'll see you. And I hope you have a good day.
You
See you
too.
tomorrow.
Thank you. Bye
All right.
bye.
Bye bye now. All right. So that's the end of that lesson there. Where were we? Let's go back here. All right. So that's the end of that lesson back there. So again, I keep saying this. I have always said this. Whenever you're solving problems, it's always a good idea to get to get through the whole idea first before you actually try to solve something. Okay. So with that, we will end this stream. So thank you for listening, all of you who are watching. There were a few people I saw who were watching. Before we end, though, don't forget that we are on YouTube. We are also on Facebook, on Instagram, on Twitch, and on TikTok. You can see the links on the screen. So with that, don't forget to like, share, and subscribe to the channels. And have a good day. Good morning, good evening, good day, good afternoon, good night, wherever you are in the world, and stay freaky, everybody. Bye bye now.